So we'll do some more propagation. The trans-equatorial one, long path versus short path, the ordinary and extraordinary waves, which is they're going to be confusing. Chordal hops are neat. Some of the sporadic E and ground waves. In trans-equatorial, you're doing a signal between across the equator. So you're going to go along a latitude line. And you have to be approximately the same distance on each side of the equator in order to do that bounce. They claim up to 5,000 miles and afternoon, early evening. I'm not sure exactly why, but maybe you've got the most ionization at that point, perhaps, because it does take some time to build it up. There's a couple examples. In one case, you're simply refracting, doing a Earth reflection around the equator, and then another refraction. I think this is trying to show that there may be cases where you have these sort of lumps in the ionosphere where you can actually take advantage of it, and it refracts through the whole thing as a single hop.
Bob?
Yes.
What do you think is the geomagnetic equator? I mean, you know what? Go ahead.
I don't know, but I guess it's like the magnetic pole. It's not in the center, so the equator is probably shifted also.
Oh, okay.
I don't know where the geomagnetic equator actually is.
Because the magnetic correction is always east or west.
Well, I would assume the equator is shifted the same way.
Yeah, I guess you're right if it's perpendicular.
I've never encountered that before.
Actually, if I remember correctly, in banking, which is equator, you have what's known as equator, but then they show you what is actually the correct.
Okay.
So yeah, they have two locations.
And that's in Ecuador.
That's in
which is named because it's like
yes.
Where is trans-equatorial propagation or TEP most likely to occur? Well, let's get rid of Charlie because we don't even know what an antipode is. And
Terminator, that's
we didn't
light and dark.
Right, gray line.
Yeah. Which
they took out. They don't have the gray line questions anymore. Let's see. Perpendicular to the geomagnetic, wherever it is, perpendicular to it.
I think this question changed, but I'm pretty sure the old version of this question was it stated 2,500 miles. Because I've talked to Chile a couple of times, and I've talked to Argentina a couple of times, and that's in the right area.
Right.
It would be a trans-equatorial hop, both fairly close to 2,500 miles from the equator.
Well, 2,500 is in that range.
Yeah, it's in that range. I'm just saying, this looks new from when I took the test a year ago.
Oh, yeah.
Yeah.
One of the things they changed.
Yep.
What is the approximate maximum range for signals using trans-equatorial propagation?
So approximately 2,500 miles north, 2,500 miles south.
How about that?
5,000 miles. Magnificent.
See, they didn't change that one.
It didn't.
At what time of day is trans-equatorial propagation most likely to occur? Charlie. Long path. Whenever you're putting out a signal, it can go, I mean, it goes in two directions, this way and that way. So one of those directions is going to be a shorter distance to the receiver than the opposite one, which we call the long path versus the short path. In the HF band, there are some cases where the long path has better propagation than the short path. I can't say I understand why, but that's just one of those phenomena. That's why this is called interesting modes of propagation.
When I was stationed in Spain, in the military, I was the one afternoon talking to a guy in Australia. And he asked me, "Oh, what's this name?" I said, "Yes, you are, I am." He goes, "I'm pointing long path to you." I was using a vertical. I think that might be the
Yeah, I think vertical.
Yep, if both of us were using horizontals, it will be almost impossible to talk from the back of the horizontal antenna. So I was using a vertical.
Um, the 20 and 40 meter bands are where it's most frequently used. They say if you're on 160, if you're in complete darkness, you can possibly do it.
Mm-hmm.
Don't know that I understand why that's true, but I believe them.
Yeah.
On which of the following amateur bands is long path propagation most frequent? Any problems? Which of the following paths is most likely to support long distance propagation on 160 meters? Delta. Sporadic E, when there's high levels of ionization and like pockets form in the E layer, which means that there's a lot of sun activity because the UV has to penetrate through the F layers to get down that far. So it's obviously in the middle of summer. That's when you're going to have the most direct. Is that a different David? Amount of sun at the perpendicular angle. So it's going to occur around the solstices in the summer. At what time of day is sporadic E propagation most likely to occur? Yeah, read it carefully because when I went through these last night, I missed that one because I read it too quick. Well, let's see. We can get rid of alpha, right? Because that's at middle of the night. So delta. Let's try delta. Sunrise and sunset during the day. At what time of year is sporadic E propagation most likely to occur?
I mean, technically speaking, what if you're like in northern latitude during some summer solstice and you got like 24 hour sun? I mean, technically it would be, you know, midnight and whatever.
Yeah, but you have a shallower sun angle, so you're not getting as much radiation.
Good point.
The guys on the equator at the solstice would be getting the maximum amount.
Mhm.
Okay. When we propagate through the ionosphere, uh, and you're sending out linearly polarized signals, either horizontal or vertical, because you're not likely to be sending circular, not rotating your antenna. It actually gets refracted, and this is kind of a new thing that they started having some questions about, this ordinary and extraordinary waves. So it actually splits into two that have different refraction characteristics. So they will refract at different angles. So even though you send one signal up, it's split into two signals at two different angles. And I don't know if it's part of that, but for whatever reason, anytime your signal is refracted by the ionosphere, it doesn't matter what the polarization was, it will come out as elliptically polarized, which means it's not circular where it's even as it rotates. It's stronger in one angle than it is perpendicular to it. So it looks like an ellipse. This was the only thing I could find, and it deals with the optics, where you have a light wave coming in and it gets reflected, and it produces this ordinary and extraordinary waves passing through that interface, which in our case would be the ionosphere, where the ionization is doing the refraction. So what are extraordinary and ordinary waves? I guess that's extraordinary and ordinary. If you want to get the maximum propagation distance, you need to have the lowest takeoff angle or elevation angle, so that when it refracts or reflects, however you want to talk about it, you get double the angle. So if it's going up at angle X, it's going to reflect at angle X also. So it gives you the maximum amount of hop. So the distance can be, you know, several thousand miles in one hop.
That's the inverse of to MBIS, which,
Canvas, yes.
yeah, that will be the inverse of it.
And how do you get in this? You lower your antenna because you want your angle to increase. What effect does lowering a signal's transmitted elevation angle have on ionospheric HF skip propagation? Charlie?
Sure.
Listen, you title up here. Oh, that's good. I didn't get rid of it. Chordal hop. it's possible to actually have such an angle that when it hits the ionosphere, it refracts and hits the ionosphere a second time without refracting back to reflect off of the Earth. So you can have one long chordal hop.
That's different from inducting? Or
Yes.
kind of the same?
No, it's different because inducting, you can have multiple hops in the duct. This is just one where, it's the angle is such that, it hits the ionosphere without touching the Earth again. And one of the advantages is, well, you get a longer hop for one thing, but every time when you have a signal propagating, every time it reflects off the Earth, you lose part of the signal. Actually, you lose more than you do when it refracts off the ionosphere, because the Earth is typically lossy. This one shows the normal hops that you would get, where if you were able to get this chordal hop, which I believe are more likely to happen at night, okay, you get this one long hop without ever touching the Earth except at the receiver.
That's completely random, right? You have no idea where it's gonna come down.
As far as I know, but I'm sure there's something out there that'll tell you when it's possible.
Bob,
Yes,
would you mind going back to that picture for a minute?
sure.
Wouldn't that has reflections from the Earth as part of the path? Oh, I see. Chordal hops are in the lower left. Okay, I didn't see that. Sorry.
Yeah, they're just showing it. Your transmitter is sending out the short path and the long path, and you're getting the normal hops. But at a certain point over there on the dark side, you actually got a chordal hop coming around. It's, to where the receiver is. So in the short
So
path,
it'll propagate farther.
yes, with less loss.
Thank you.
Did we do this one?
I know. Yeah.
So what is chordal hop? Bravo. What is the effect of chordal hop propagation? What's different about it?
I'm gonna reflect that curve.
You don't have the loss that you get from the Earth reflections. Oh, I just left this chart here. They don't have a question anymore, which I don't like. Just so you know what the gray line is, let me mention the terminator. It's it's the terminator as it goes between light and dark around the Earth, and there's a propagation mode where you can, if you're on the gray line, you can contact another station on the gray line because it'll propagate along that day-night terminator farther. And this is just showing, what the terminator looks like. Ground waves are waves that propagate parallel to the Earth and adjacent to the surface of the Earth. So they go along the Earth, and they curve. And that's one of the effects when we talk about radio horizon and line of sight, where the radio horizon uses some ground effect and actually will go farther than line of sight because it will follow the curvature of the Earth. It works better at lower frequencies. You get more loss the higher the frequency. So you normally see the ground wave stuff at the low end of the HF. And it works best with vertical polarization. So if you got a vertical antenna, you're more likely to see ground wave propagation. What type of polarization is supported by ground wave propagation? Vertical. How does the maximum range of ground wave propagation change when the signal frequency is increased? It decreases.